Okay.
How's everybody doing?
Tired, but good.
Yeah.
Did you have your exams yet?
One. So,
No,
I gave a
I got
final yesterday at 8.
Wednesday,
Huh?
Thursday, Friday. All at 8 o'clock.
ooh.
I don't know how many people are going to show up.
Some can't make it, but yeah.
Yeah,
That's-
there's a few that said they had a EMAG final right now.
Mhm.
Oh,
And I know Nick has a test today as well at 12, so
at 12?
at 12. But anyways, so a few questions.
Okay, let me get my doc cam. I got to share a screen and get this document camera up. And my camera. Should work. May have to restart it. Hey, Lydia, admit me, buddy, if you come in.
Sounds good.
You should see a yellow tablet. I hope. All right. What are the questions? Go ahead.
So firstly, more of like general questions about the test.
Mhm.
What is the point breakdown going to be like? I knew that you said there's going to be a different.
I haven't made the test out yet completely. It's probably going to be 6 questions and it'd be each worth 1/6 of the final score. So
Okay. All right. So
I don't-
out of 60, I guess.
I guess, yeah, something like that. There are multiple.
Okay.
And
So,
I mean,
like,
any technical questions about the material?
a non-technical question, sorry again, but
Alright.
like another person was asking so are you going to like distribute the test by email again?
Yeah.
Like
It'll
last
be
time?
just like the last exam. I'm going to email everybody. Probably I'll about quarter to 8, 7:30, quarter to 8 tomorrow. You should receive it, and I'll give you 3 hours. All right.
Okay.
And then you'll have time to go through the technical problems of uploading it back to Canvas and taking care of that. So it shouldn't be a problem.
Okay.
It's like the same type of test as the last test. The problems are more involved, but if you know what you're doing, you should fly through it.
Okay. So another question that I had was like about modulation with Z transforms. So I knew that you went over like a cosine in one of the earlier lectures, but I'm not really sure if there's like a specific format that you want like the cosine and the sine to go into when you're doing a Z transform.
Well, it's modulation, and I mean, you can see this, but anytime you have a Z transform, what happens? I'll direct you to let's see, right.
One question I have is, can you do the modulation in the S-plane, or do you have to convert it to the frequency domain before you do the modulation?
Well, there's a couple of questions here. S and T have to do with Laplace transforms.
Right.
And, we're talking about Z trans EFTs, I think is what Lydia's talking about. And
Yeah, so it has to be in the frequency domain.
Well, when you talk about modulation, it's written in the time domain. For instance, if I'm just going to show you this. You have x of t, right? And it's times cosine of omega naught t, right? That is a time domain function. I hope you can see that.
Yeah, okay.
It's written in the time domain. Now, what does it look like in the frequency domain? Well, if x of t had this spectrum, and I'm just going to draw it, if it had a spectrum like this, if that was x of omega, then if I multiply it by cosine of omega naught t, what it does is take this spectrum and it spreads it at plus or minus omega naught. So it would take this thing, and if you went to minus omega naught plus omega naught, we take this very thing and just move it here and here. You follow me on that? The way you're used to seeing is they don't have them skewed, they have it like this. And then you would see this would be centered there. But whatever the x of omega is, it's just shifted out to plus and minus omega naught. So this point right here would go to omega naught here and here. Can you follow what I'm doing here? Try to be a little neater about that.
Yeah.
If I had a signal x of t here, and it went to this is x of omega. Now, if I multiplied x of t times cosine of omega naught t, what would happen is at minus omega naught and plus omega naught, you would have this divided by 2. It would be x of omega divided by 2. And this would be a magnitude spectrum. And this would go down to x of omega over 2 magnitude. So it's just split up and down the axis. Now that's true. This is continuous time. What she's asking about is if you had something and it was in discrete time or discrete points. And if I had like x of n, and say just for the kicks, x of n had this type of response. This is versus capital omega. Well, then if I have x of n times cosine of omega naught n, now what happens, this 0 point here, it will shift to, and the magnitude, if that's 1, this will be 1/2. Basically, the replicas are placed at plus or minus the point. And I think everybody knows that. This is basic modulation theory, right? That's it in a nutshell. And if you look for your...
Could you possibly do a numerical example with it? Or
Well,
with cosine and sine?
Sure, we can do one. If you had, for instance, this. Why not? Suppose I had x of n equal to 1/2 n u of n. It's a simple function, right? Now I know that that has an x of omega. I can do it x of z if you want. It doesn't matter. X of omega of what? That's equal to 1 over 1 minus 1/2, right?
Mm-hmm.
E to the minus j omega. Do y'all agree with me?
Mm-hmm.
Now, if that's x of omega, and that's x of n, then x of n times cosine of omega naught n, and maybe I'll put an omega naught here. Suppose it's x of n times cosine of, say, pi over 2n. Are you with me? Now, the cosine is multiplying this, so it's modulation. Well, that would be, take this waveform, and what I end up doing is going to minus pi over 2 plus pi over 2. And I would say that the formal way to do this, now I could draw what this looks like, but just take this omega right there I hope you all can see that. And just replace it by omega minus pi over 2 and omega plus pi over 2 and divide out 1/2 in front of it. So this function, the modulation of this would be 1/2, and then it would be 1 over 1 minus 1/2 e to the minus j omega minus pi over 2, and it would be plus 1 over 1 minus 1/2 e to the minus j omega plus pi over 2. You follow me on this? The only thing I'm doing is taking the original one here and just replacing this omega with a omega plus pi over 2 and omega minus pi over 2, and then putting 1/2 out in front to scale it.
Mm-hmm.
Right? That's the modulation property in a nutshell. And if you wanted to do with Z transforms, it's the same. It's just that instead of, then you would do what? If Z, then modulation does what? X of n times cosine of pi over 2n. That becomes 1/2 times what? Well, then it's x of what? Z, right? Times what? It's z times e to the j pi over 2 plus x of z times e to the minus j pi over 2. Remember doing this? I got some people. Good minimum.
Mm-hmm. Yes, sir.
How many do we have here? Okay.
9 students, I
Okay,
guess.
9. What else?
So you could do something similar with sine, I'm assuming?
What happens with the difference between sine and cosine in the time domain? If I have x of t times the sine of omega naught t, what's the difference? Remember? And this is, it's supposed to be a sine. X of t plus t times the sine of omega naught t. What happens there? Now it's going to be what? J over 2, right?
Mhm.
Remember, there's the phase, and then it's going to be x of omega plus omega naught minus x of omega minus omega naught, right?
Right.
So the magnitude spectrum is identical. The thing is, the phase spectrum is going to have a j. That's a 90 degrees, right? And then it will not be additive, but it will be subtracting.
Right.
With me? That's the
So in the z domain, that will be j over 2 z to the e j pi over 2 minus.
But it's the same exact thing as this, except there's a j here. This is a sine, right? If that was a sine, then there would be a j over 2. I'm sorry, it's messy. This would still hold, only this would become minus, right? I don't see this, guys.
What becomes minus? Sorry, my internet's being a little bit unstable.
Well, what happens? The plus sign becomes a minus sign.
Okay. Okay. That
Y'all
makes,
with me on this, guys? This is tricky. It's fairly straightforward. I'm sorry. It's but that's general modulation. And you can play with this. You can do it. You can do all sorts of things. Modulation, and there's a lot of material to draw from, both the book and on the internet about this stuff.
okay, that answers my question. Thank you.
Yeah, if you look at page 226, bottom left in the book, that's the modulation properties.
226.
Yeah, 226, bottom left.
Okay.
No, that's not modulation. That's just cosine and sine. They're multiplied by 1. All right, now you can. I can
So that's
show
not
you.
doing the plus
If you
omega
want it-
minus omega?
Those are delta functions there, right? If you want to do this, I'll show you the trick here. Fine. All right. Now delta of t goes to what in the frequency domain? 1, right? That's for s or a small omega. Isn't that right, class? If this is x of t, this would be x of
Can
omega,
you
correct?
scoot it down a little bit?
Sorry, thank you. X of t would go to, if x of t was delta t, it would go to 1. Do you all agree with that?
Yes.
Are y'all seeing this or not? All right. Now, if we use what? If we use duality, then 1 would go to 2 pi delta of minus omega. And because minus delta of minus omega is the same thing as delta of omega, just put plus omega, right?
Mhm.
All right. Now, think of this as x of t. All right. Now we use modulation. Modulation says if I have x of t times cosine of omega naught t, that goes to 1/2, right? Times x of omega plus omega naught plus x of omega minus omega naught, right? Y'all see this? This is straightforward. There's absolutely nothing tricky about this. And if you've been keeping up with this, this should be pretty obvious by this time. So now I have, this is my x of t, this is my x of omega, right? Are you with me? I'm assuming 1's there because what is the actual property that they have, the cosine of omega t on the bottom of page 226? They want to know what cosine of omega naught t goes to. Well, the multiplier is 1. 1 is my x of t. Are you with me?
Mhm.
Now 1 we know goes to 2 pi times the delta function. Well, 1 times cosine of omega t goes to 1/2. Then what is x of omega? Well, it's 2 pi times delta of omega, only we replaced the omega by omega plus omega naught. So I'll take the 2 pi out in front, and I get what? I get delta of omega plus omega naught plus delta of omega minus omega naught, right? And you can see the 2's cancel, so you really get pi times delta of omega plus omega naught plus delta of omega minus omega naught. And that's the property, I mean, that's what they show on the bottom of that page. That's cosine omega naught t, but it's not the modulation property. That is just
I
an
got
actual
you.
transform of cosine omega naught t.
Okay. Yeah, modulation's 230.
Yeah, right. Good. I wish he buried that in the actual properties list on his tables, but he doesn't have that one. That's the tables are 229. Y'all with me, guys?
Mhm.
And that's true in discrete as well as continuous. So, what else? I don't know about you, but I've had about my share of Zoom meetings. Ready for a break.
I was wondering if you could go over 3.18b in the book.
3.18.
Yes, 3.18 part B.
B as in boy.
Yes, the letter B.
All right. They have, I've just got to write all this. They have S minus 8. And what's they have e to the minus 6s, right? Over s plus 2, s squared plus 60. And I want to transform. Well, I can see right here, I have a double pole, don't I?
Mhm.
And I also have this, that irritating one. Right? What I'm going to do for starters is just ignore that. I'll put that in later because I know that's a simple. I mean, if it's a phase in frequency, it's a shift in time. Is it, class?
Mhm.
Correct? All right. So now, question is, how do I do this? S times S minus 8 over S plus 2, S squared plus 16. So how do you want to do it? Well, I think it would be smart to try to do a expansion, partial fraction expansion, right?
Mm-hmm.
It's up to you how you want to do this, but let's see here. I can say that some constant C1 over S plus 2 plus, and here I got a double pole, so I got a squared operator, so I have to put S squared plus 16, and then I have to put, that's C1, I'll call this AS plus B. If this, whatever the order here is, if this is an S squared, there has to be a single S here. If it was S cubed down here, there would have to be an S squared here, and there has to be a constant times S plus just, a constant times S plus just B. This is the way you do this. If you remember when you did Laplace transforms in your
Dr.
math
Baginski,
courses.
quick question. Could you make S squared plus 16 into S minus 4 times S plus 4? And then
Yeah,
do partial
actually,
fractions?
you can do that. You could do.
That would make
You're
it
ahead of me on
S
this one.
squared minus 16.
Yeah, it's S squared minus 16.
Oh, right. That's right. That's true.
Well, I mean, this, yeah, you're absolutely right. I'm going to just continue on with this over S plus 2 over S squared plus 16. Now, I'm going to just tell you this. Anytime I see an S squared plus 16 at the bottom, I know I got a cosine or a sine on the other side. And I don't know where the tables are for this stuff. I don't know. A second here. All right, if you look on page 97, you're going to see the sine omega naught t goes to omega squared, or omega over S squared plus omega squared, and a cosine of omega naught t goes to S over S squared plus omega naught squared. But you can have a combination of the two. Y'all agree with me there?
Mm-hmm.
All right, so I'm going to go ahead and say this is really C1 over S plus 2 plus AS plus B over S squared plus 16. I don't know how the book does it, but I'm going to ignore this term right now until the very end. All right, y'all with me on this class?
Mm-hmm.
All right, somebody go ahead and help me. How do I get C1? What do I do?
We do cover up
Plug in -2.
and then
Yeah, cover it up. And what do I do? Evaluate the rest of that at S equals
-2.
at S equals minus 2, right? And what would it be? C1 would be equal to minus 2, right? And this would be minus 10 there, right? And then it would be minus 2 squared on the, was going to be 4 plus 16 is 20, right? Or this would be minus 1. Y'all agree with that? Guys? What about, hang on for a minute. For this part, what do? I mean, there's a lot of ways to do it, but I mean, I could use it. I think I can multiply through and do the derivative. Probably the way you're going to do it. I can't guarantee this, but I'm going to just get a common denominator here. I already know C1 is minus 1. So then I have S minus 8 over S plus 2, S squared plus 16 here. And I know that's going to be equal to C1. And I'm going to replace C1 with minus 1. And that's going to be times S squared plus 16. I'm getting a common denominator over here. So S plus S squared plus 16. And then I have plus A S plus B times S plus 2. Y'all with me? What I've done? Got a common denominator, right?
Mm-hmm.
Now I have to take this and equate this to this. So I have, what was that? S squared over here minus 8S, right? Plus 0 equals, and I'm going to see if I can do this right. Let's see. I got AS squared minus 1. So I have A minus 1 S squared. I just took 1 here. Minus 1 is the coefficient S squared. And AS times S right there would be AS squared. Correct, class? Y'all see this? So this is an equation, and I can obviously see that A minus 1 has to be 1, right? You see the coefficient of S squared is 1?
Mm-hmm.
Y'all see that, class? So that means A is 2. So I know A is 2, don't I, class?
Mm-hmm.
What about the next part? Well, if I take a look at where B is, B times S, right? And then there's AS. What I'm looking for is I need to get B involved right here. And if I take a look at this, if I take a look at the power of just S, I have AS times 2, which would be 2AS. 2AS, and then
Or plus
plus BS right here, right? That's the inner one. And I don't have any other single things. That has to be equal to minus 8S, right? So minus 8 is equal to 2A plus B. And I know A is 2. So that's minus 8 is equal to 4 plus B. Y'all agree with that,
Mm-hmm.
guys?
Mm-hmm.
And then in the end, I know that B is minus 12, right?
Mm-hmm.
Y'all see this or not? I'm trying to see you guys, and I've got you pushed over to this edge. I don't see most of you. It helps if you turn your cameras on. I can kind of get a read. You don't have to, but it helps me. How many people do we have here?
9.
Okay, good. Now, you've got these coefficients, right?
Mm-hmm.
So C1 was minus 1 over S plus 2. Then A was, what was A? 2, right? 2S over S squared plus 16.
Can you move it down?
Yeah. And what was B? Minus 1? 12, right?
Yes.
Over S squared plus 16,
Dr.
correct?
Baginski, quick question on the previous page. Wasn't it S squared plus 16? And where did the negative 16 go? Did you move it over to the other side? Since like if
On this
you
side, there's no,
distribute,
what?
and you have
Well, I'm just looking for the
-1.
powers. See, I'm looking for
Okay.
the coefficients of S squared, the coefficients. This is S times S minus 8. So it'd be S squared
Right.
minus 8S
Right.
and 0. So I'm
Mhm.
taking the coefficients of S squared on this side. That's going to be just A minus 1 and equating them to 1.
Right.
I'm just equating the coefficient
Okay.
powers.
Okay.
I'm not rewriting the whole equation. Can y'all see
All right.
that? Y'all follow me on this, guys? This is straightforward stuff. We've been doing this for quite a while. So this is what I got when I do the expansion. I know I didn't put in the exponential term yet, but what do we know this goes to? It's not looking. Minus what? E to the minus 2t u of t, correct, class? Right? Now, what about this one? Well, this one's a little bit different because what are we used to seeing? We're used to seeing S over S squared plus omega naught squared going to cosine omega naught, right?
Mm-hmm.
But there's a 2 there, so that's going to be what? Plus 2 cosine of 4t u of t, right? We know that the 16 is omega naught squared, so 4 would be omega naught, correct, class?
Mm-hmm.
What about this? Well, we're used to seeing what? We're used to seeing omega naught over S squared plus omega naught squared goes to a sine of omega naught t, correct? T.
Mhm.
All right, well, for this one right here, the omega naught I have to have up here, I have to have by itself 4. So if I look at 12, 12 would be 4 times minus 3. So this is going to be minus 3 here times the sine of 4t u of t. Y'all agree with that, class?
Mhm.
Yeah.
And again, there's nothing tricky about this, except that you can confuse yourself in making it far more complicated if you just don't realize, hey, if I got an s squared plus a constant right there, that's definitely a sine or a cosine.
Mhm.
I know that. And the other one's a simple pole. Now, all that right here is x of t. But what happens when I have x of t minus alpha? That goes to x of what? If you want it, x of s times what? E to the minus alpha s, correct, class? So if this is x of t, I have to take this t here and replace it by, I think it was e to the minus 6s. Wasn't that the operator I ignored?
Yeah.
Mhm.
So you're just going to replace all these t's here with t minus 6. And that will give you. You agree, people? I'm trying to make this as obvious as I can. It's not very hard to see, but if somebody tries to brute force that right off the bat, you're going to get in trouble. Let's leave that alone to the very end, okay? Now, is the answer in the book different than what I did? And if it is, I can mention this. You can add these sines and cosines and create just a sine or just a cosine with a phase difference too. But I prefer to break it out into a sine and a cosine. Huh? Somebody said?
Yeah, I mean, I just plugged it into Wolfram Alpha and got a little bit different answer.
Well, you can just get a sine or just get a cosine with a phase angle. I hate doing it that way. I prefer not to do it. That's when you expand with complex poles.
Right.
This is an adequate and sufficient answer. That's right. All right. Okay. What if I did this? Well, I'm better. I'll stop. I can see if I make some suggestions. This problem could be a 3-hour problem. Okay. What next?
Quick question about this one. So the shift at the very end, that was because of the e to the j omega up top that we canceled out.
Not e to the j
anyway.
omega. It's e to the minus s, 6s, right? There's no
Well,
j.
I think it was in the very in the initial
In the problem statement, it had what? It had e to the minus 6s, didn't it?
Oh, okay. All right. Yeah.
There's
sorry.
no j at all.
I got you. Okay. Thanks.
What else?
I was wondering if you could do like a filter type problem.
Okay. Which kind of filter?
I guess one where you ask like, oh, what are the poles and zeros? Like, what is the type of filter, like low pass, high pass, band pass? And then I guess.
All right. You got a page you're looking at, or just want me to come up with something?
I just come up with something. I think that would be good.
All right. You want to do this in S or Z?
Z.
All right. So this is the Z plane. And I'm going to draw the unit circle out here. That's 1. All right. Now I'm going to do something. I'm going to put 2 poles here. They're inside the 1 circle. And I'm going to put 2 zeros here. You know what? You know, this right here is really 1 e to the j omega, isn't it? That's 1 at an angle of omega, correct? And omega goes from 0 to 2 pi, doesn't it? With me, guys? Okay, so what kind of filter is it? Say these things are 0.8 e to the j pi over 10, and this is, or make it degrees. I'll just take it 0.8 e to the plus or minus j 20 degrees, and make these zeros at, say, plus or minus 139. So this zero is going to be at 139 degrees. This one's going to be at minus 139 degrees. What kind of filter is it? Tell me the reasoning. Anybody?
Low pass.
Well, what do you know about filters? Where the poles are is where they pass, right? All right, those
Below.
poles are at very low frequencies, aren't they? I mean, they're at low angles. Small angles equate to low frequency, correct, class? All right, it's passing low frequencies, and the zeros are getting closer and closer to pi, right? So it's stopping high frequencies. This is a low pass filter. Y'all agree with that? And if you wanted, if I gave you this and I said, well, I want an equation for this, and I want you to scale it so at 0, it has a value of 10. Just say that. Well, you know what you're going to do. You're going to put what? It's going to be, you can do it in the z domain if you want. You can just write e to the j. Want to do it that way. E to the j omega. Now that's a 0, so it's going to be minus e to the j 139, right? And then it would be e to the j omega plus, I'm sorry, minus e to the j minus 139, right? Those are the zeros. And downstairs it would be e to the j omega. Here, these are poles, and it's going to be minus e to the j, oh, sorry, poles that got a weight of 0.8, right? E to the j 20 degrees, and then it's e to the j omega minus 0.8 e to the minus j 20 degrees. And then put a constant k out here. And that's my filter in a nutshell, right? And I could have used z there. I didn't have to actually write e to the j omega, but I know in a frequency, if I'm getting an h of omega, if I wanted a frequency domain plot of this, then I would let z become e to the j omega, correct, class? By the way, is this stable?
Yes.
Absolutely, isn't it? Because why? The poles are inside the one circle. Y'all agree with that?
So if a pole was at the very border of the one circle, so would that be
Marginally stable.
okay?
But I try not to go into that too much. That's the thing that a certain type of input could cause an instability, but it's marginally stable. It's just like if you put a pole on the j omega axis in the S-plane, well, what you get is something that is marginally stable. It will actually never go to infinity, but it will never ring down to 0 either if you hit it with an impulse function. So that's the difference. Now, I'm going to tell you, this would be an equation, right? But if you wanted to evaluate this at 0, this is the important thing. Now, you have calculators, so you could, if I wanted this at 0 to be a value of 10, then you would put 10 on this side would be equal to k. Now, e to the j 0 is 1, so it's 1 minus e to the minus j 139. And it would be 1 minus e to the plus j 139, right? And you have to evaluate these. And remember, by the way, I'm putting them in degrees. Usually, if you would want to put these in radians. I'm just putting them in degrees because it's easier to understand degrees. Generally, people have a very good understanding of 20-degree angle, but a pi over 20, not so much. Pi over 2, yeah, pi over 4, they don't know 90, 45. They know pi over 3 is 60. But when you get down to pi over 20 and stuff, there's a lot of uncertainty. Then you put the zeros down. So remember, e to the j omega is 1, so it's 1 minus 0.8 e to the j 20, and 1 minus 0.8 e to the minus j 20. And then you would have to evaluate what that is for k. You'd have to invert that, multiply by 10. And I have no idea what that is. But it's going to be a complex number, I think. I think. I don't know. Y'all see this, class?
Dr. Baginski, I'll be away from my laptop for a minute. I'll be right back.
Yeah, go ahead. What about you other guys? Chad, Aaron?
I have
Ruth?
another question
Okay,
that's not about this, if that's okay.
yeah, go ahead.
On the homework number 25, 717E, I can just read it to you if you want.
Yeah, what's it about?
It's Z transforms.
Okay,
Or inverse transforms actually. So it's given Z squared minus Z over Z squared minus 2Z plus 2.
+2?
Yeah.
So what do they want?
The inverse transform of that.
All right, first thing I'm divide top, and I'm going to divide the bottom and the top because I see they're the same order. Now, you don't have to do this. Remember, the trick with inverse was if this is x of z, what you do is get x of z by z. That would be z minus 1 here. And then z squared minus 2z plus 2. Let's see, how could we make that work? Would that be... I'll just z squared minus 2z plus 2 here. And
Dr. Baginski, can you like complete the square on the bottom to get z minus 1 squared?
I'm thinking about getting a z minus 1 out of there, and but let me just look at this for 1 second.
Yeah, z minus 1 squared, you just have an additional 1, a constant of 1 extra, right?
That gives you z squared minus 2z plus 1. Well, let me see what's that going to buy us. So z minus 1 here squared, and then you'd have to have a plus 1, right?
Yeah.
I'm not sure it's buying me what I want. Ruth, what problem was this again?
It's 7.17E on homework 25.
Is that a book problem?
It is. They use like the 1 plus J, 1 minus J stuff. And
Yeah, and that's a complex pole. I tend to I don't like that. But what is 7 point what again?
17E.
If I get down to this point, my real problem. I don't think in the tables. Yeah, he does. Okay. I'm just going to show you what he's looking for. I'll just show you this. You see how this right here, cosine omega n u of n goes to this?
Yes.
All right, now that means the cosine of omega here would have to be 1. Follow me?
Uh-huh.
And if it was 1, then I'd have z squared minus 2z plus 1. What do I have in my bottom? Z squared minus 2z
Plus 2.
plus 2. And that means I have an a to the n in there. Let me just take a look at this for a second. So this would be z squared minus a times cosine of omega has to be 1. Here's how I'm just telling you to do it. I'm fitting this form right here. I'm not going to fuss with it because the way I'm going to do this thing will not involve this. It would be a completing the square operation, but what that means, I'm going to get both a sine and a cosine times an a to the n. Here, maybe I'd probably only get a cosine when I think about it. When I do this and I look at this, I know that a times cosine omega has to be equal to 1, right? Coefficient b on top. And if that's the case, I also know that a squared has to be equal to 2, correct?
Mm-hmm.
That means cosine of omega is 1/2. Agree with me?
Yes.
And if cosine omega is 1/2, then omega is pi over 2. Or sorry, pi over 3, correct?
Pi over 3, yeah.
And if it's pi over 3, that would be cosine of pi over 3n, and a would be a 2 to the n right here, correct?
It would be what? Sorry?
2. A is 2, right?
Yes.
All right, so if that's 2 to the n, that's an unstable response, by the way. Right?
Okay.
It's growing it's growing geometrically. It's going to blow up. That's a trickier problem, but you can match forms. You'll have your table.
Wait, was a 2 or root 2?
No,
Wouldn't a squared
if
be
you
2?
take a look at this, just take a look at the coefficient here. A times cosine of omega has to be equal to 1, right?
Uh-huh.
But down here, a squared, I'm sorry, you're right, Ruth. A squared was equal to 2, so a would be square root of 2. You're right about that.
Which is still greater than 1, but just making
Yeah,
sure.
and it's going to be unstable. It's going to grow exponential. It's going to grow geometrically.
Okay.
But I just equated on that one. I wouldn't mess with it. What I was thinking about doing, and I don't do this for this class, but if you get down to this form right here, you remember back in the day when we completed the squares, when we had like e to the at. This is an autofocus, but sometimes autofocus is not an autofocus. When we had at times cosine of omega naught t, u of t, what happened over here? In the S domain, what was it? It was S what? Plus a over S plus a squared, right? Plus omega naught squared. Do you all remember that?
Yes.
All right, well, in the Z domain, you have an equivalent of this. Now, you're going to get a cosine of an omega naught, and this is going to be a to the n, and you get those by doing equation. But I don't want to take you down that route because I haven't showed the rest of the class this method. I'm not going to hold you responsible. We didn't cover it. Don't worry about that. Okay. What else? That's a more difficult problem, by the way. If you try to do that longhand, you're going to get two complex poles, and that's a pain.
Dr. Baginski, on the previous filter problem you worked, where you put a 10 off to the side, you said that would be like in what case would you put that 10?
If I told you the magnitude of the filter was 10 at omega equals 0, then once you had the filter response, you'd have to calculate that constant k to get it equal to a magnitude of 10.
Okay, I got
you. Where are there more filter problems like that in the book?
Well, yeah, let me just show you. This is a pseudo filter type problem. You see, there's all sorts of block diagram problems, and they are filters. Anytime you have block diagrams, that represents a system operation. You could call it a filter. And remember this, anytime I have a difference equation, technically that is a filter as well. It's a filter operation, an output based on an input. Anytime you have an input and an output, be it block diagram, differential or difference equation, or transfer function, they're all basically filter operations. They take the input, they do something with it to get the output. It's a linear time invariant system. Okay.
I had one other Z transform question. From homework 24. Would you rather me read it or look at it? It's
Let me see if I can find it.
complicated. It's 7.15D in the book.
$7.15. What? Say that again.
15D, as in dog.
Give me a second. Oh. All right. Correct me if I'm wrong. Right here.
Yes, that one.
All right, I'll tell you what I'd do right off the bat. I take that 2 to the n plus 1 and just make it 2 times 2 to the n. You follow me?
Okay.
That's the first thing I do. Now, after that, this is dependent on how you feel about this. If I just have a to the n cosine of omega naught n plus a phase angle, I can go right to this is the one advantage you have, that you're not going to have to do a lot of fussing with them. And in the Z transform tables, if I can find them, I can see that if I have a to the n times cosine of omega n plus a phase angle, that goes right to this thing with those complex arguments.
Oh.
That's the
I didn't
bottom,
even see that.
7A on page 368. Got your
So that's
book?
property 7A, right?
Yep. And
Yeah, I
that's a
totally-
no-brainer then, right?
totally
It's
missed
just
that.
recognizing forms. That's why I don't like, I do not like giving open book tests, because it's really just how fast you can search your book for something half the time. That's why when I'm making out these tests, I'm going to make sure it won't be something where you just look, oh, there it is. All the problems are constructed differently.
Can you explain what a conjugate is again, real fast?
Yeah. And by the way, there are no dumb questions, because that's when it gets dangerous, when people are afraid to ask a question because they'll be laughed at. And if anybody is in the military, one thing you know is you never ridicule somebody for a question. It's obvious, because that's when people get blown up. Stuff like this. They don't know. Don't pull the pin in the grenade until you're ready to throw it. Then you have 3 seconds. Things like that save lives. And in general, there are no dumb questions. Now, if you start talking about football or something like that, that's a dumb question. But if it's anything to do with this stuff, it's okay. And conjugation in general, I'm going to create a number. If I have 1 plus j5, that's a complex number. Real part is 1, complex part is 5. That can be written as the square root of 1 plus 5 squared, square root, right? So it's really square root of 26, and it would be e to the j, and the angle would be an inverse tangent operation of 5 over 1, right? I don't know what that angle is, right? Now that's a complex number. I went from a real and imaginary part to a complex number. If I had a number, say 10 e to the j 20 degrees, and I wanted that in terms of a real and an imaginary part, that would be 10 times the cosine of 20 degrees plus j 10 times the sine of 20 degrees. Y'all remember this, right? This is using Euler's identity for e to the j 20. So when I'm doing conjugation, if I have a equals 10 e to the j 20 degrees, a conjugate is simply 10 e to the minus j 20 degrees. Just flip the angle. With me?
Mm-hmm.
Over here, what it would entail is you just change the sign on the imaginary part. So I've already written that out. The conjugate would just be 10 times cosine of 20 degrees minus J10 times the sine of 20 degrees. Okay?
Okay. Okay. Thank you.
That's it. Other questions? I didn't get a lot of sleep last night. I was so, my upper back, or it's called a torn rhombus muscle, and it's under the trapezius muscle, and it just bugging me lately. What else do you have for me?
Can we do a Fourier series with this circuit?
Sure, why not? You got one in mind?
Not anyone in particular.
Not one in particular. All right. Yeah, sure, why not? Let's do Fourier series. So first, let's just talk about Fourier series. In general, if I had something like this, this goes on forever. And this is, say, x of t. And say that's 2, that's 1, the height is 1. So this is a periodic function. The period is 2, right? So t would be 2. Omega naught would be 2 pi, right, over 2, or simply pi, correct? I would look at that and I could say C0, the average value would be 1/2. I mean, you can do that with your eyes. You don't need a math equation, correct, class? After that, I need the Fourier series. So what am I going to do? Now this is the make or break. If you don't know this next step, you probably haven't been paying attention. What's the next step? I know this x of t, by the way, is equal to what? A summation of c of n e to the j n omega naught t. N goes from minus infinity to infinity. Y'all agree with me there? I know that, and I know what c of n is in general. It's 1 over t, the integral from 0 to t of x of t e to the minus j n omega naught t dt. And it's messy, but you know what I'm doing. I'm sure you've done it over and over again, right? So what do I do? The next step, guys. Aaron, go for it.
Derivative.
And what do you get?
There would be impulse at 0 of.
And it's repeating series, right?
Yeah.
Impulses have magnitude of 1, right?
Mhm.
This would be at 1, at 2, at 3, and so forth. Y'all agree with that? Guys, so what am I going to do next? I know that my x prime of t is equal to an infinite series of c of n prime, right? Times e to the j n omega naught t. N goes from minus infinity to infinity. But what is my c of n prime? Guys, it is 1 over the period, right? Now you got to be careful. You want, technically, if we go from 0 to 2, the period, I hit these things right when they're coming up or going down, right? So what I do is move my window of integration over so I don't land on one of those. So it has to go over a range of 2, but now I started at maybe minus 0.25 and end up at 1.75. Y'all follow me on this? And now I get my c of n prime. It's that, and then when I do the integral, I have 2 delta functions. I have a delta of just t, and then I have minus delta of t minus 1, and they're times e to the minus j n omega naught t dt. This is going to go from minus, say, a quarter to 1.75, but you don't have to be that exact. I'm just writing it to show you that mathematically what I'm going to do. Because you can do this with your eyes, just taking a look. C of n prime, therefore, is going to be 1/2, right? The delta function at t equals 0 turns on at 0, so I simply find out what e to the j0 is. It's 1, right? And what coming up next? Then it's going to be minus e to the minus j. Well, it's going to be what? When does this turn on? At 1, right? So I replace t with 1. So it's e to the minus j n omega naught. Correct, class? Are you with me, everyone? But I'm not quite done yet. What do I have to do to get my C of n?
Divide by Jn omega naught.
That's right. And divide by 1 over j n omega naught. Now I have my C of n. For all values of n except 0. At 0, I have the other one, right?
Mm-hmm.
All right. And I'll assume that you see how omega naught is pi, and I can put it in there. And I could turn this into a sine function if I wanted to manipulate it, but I'm not going to manipulate it. I'm just saying you could do that. Now I'm going to go and say that, because it's a circuits problem you want, right?
Yes.
All right, so if it's a circuits problem, I got to create a circuit. So why don't we make a circuit? How about we do this? You guys should be pretty good at circuits. You had Irwin especially.
Could you scoot it down a little bit?
Yeah, I'm just making up the circuit. So this is L, R, and C, right? Now I want the transfer function. I like using the transfer function in the S plane. So now I'll put this as SL, right? And this is 1 over SC. You can put values for anything. You can come up with values for C and S and R. This is general, correct, class?
Yes.
Now I need my H of S. What is H of S? It's this impedance, right? Over that impedance plus R plus SL, right? Then we can play the game where we want this in the form of S squared plus AS plus B. It's really, if we want that, I have to multiply top and bottom by S first. And when I do this, I have 1 over C. And then I have S squared L plus RS plus 1 over C, right? And then I divide everything by L. Right? And that's my filter response in the H domain, or in the S domain. And then I let S become J N omega naught, right? Because this is the 40 series problem, right? All right, and you know the drill here. I'm not going to go ahead and do that, but you can see that you're just replacing S by J N omega naught, correct?
Yep.
Everybody? So now you get your filter response. Now I can say that Y of t will be equal to C0, with the average value, times H of 0. What is H of 0, by the way? Take a look at this. When S is 0, what do we have? 1 over CL, 1 over CL are 1, so it's times 1. Plus, and this is going to be a single-sided cosine series, n goes from 1 to infinity, infinity of 2 times magnitude of C of n. We got that from before, times magnitude of this filter at n omega naught, right? And then it's times the cosine of n omega naught times t plus the phase angle of C of n, whatever that is, plus the phase angle of H of n omega naught. And that would be the actual filter. And that would be the output Y. Now, if you wanted specific values, we can do it. If I could say, and this is the question I asked last time, if I said I want the magnitude of the 10th harmonic or the 5th harmonic, say the 4th harmonic, what I'm looking at is the value of this, the magnitude of that when n is 4. Okay? How many people do we have here, guys?
8.
8 students plus you.
All right. I mean, you can turn your cameras on. Obviously, some people don't want to do that because they're either, I've got kids in the other class, one in particular, he's got a real long beard, hair is just down to here. Half the time, like I'm wearing beat up old t-shirt today, and I really don't care.
So could you do one with like a magnitude and a phase plot, for example?
Well, let's just do magnitude of phase of this one, right? We've got this. Pick some values. How about we let C and L be 1, all right? And for kicks, let R be 1. So we have this. We're going to have H of S equal to 1 over S squared plus S plus 1.
Could you move the paper up, please?
All right? I'm just showing you L and C and R 1, you get that, don't you? All right, now we want magnitude and phase, but first we have to say we're going to let S go to just J omega. I'm going to do this in continuous frequency. So now my H of omega would be what, guys? It would be 1 over, well, J omega squared is minus omega squared, so I'd have 1 minus omega squared here, and then plus J omega, correct?
What? Could you guys say that again? I'm sorry.
What is, if you replace S with J omega and square it, what happens? What is J squared?
-1.
Minus 1, that's where it's minus.
So -1 plus
We already had 1, right? 1 minus omega squared. That's the real part. The imaginary is J omega. You agree with me? Everybody?
Yep.
All right. So how do I get the magnitude of that? Well, what do I do? Take 1 over square root of 1 minus omega squared plus, and this would just be omega squared, right? Y'all give me that one? All right. Aaron, how do I get the phase? You're there? You look in a productive mood today.
Yeah.
So if I had H of omega is equal to 1 over, and what was that again? That was 1 minus omega squared plus J omega, right?
Yeah.
All right, how do I get the phase of that? Oh, my other class would say I'd Google it.
I'm not quite sure.
You are. Isn't this just a real and imaginary number, right?
Right.
So what is this? If we wanted the phase, that'd be 1 over, well, what's the phase of that? That's tan minus 1 of omega, that's the opposite J, right? Divided by adjacent, 1 minus omega squared, right? But it's the inverse tan or arctan, right? That's an angle. You all agree with me?
Mm-hmm.
Can you all see this, people? But what happens when you take an angle and bring it up top? It becomes minus, right? Tan minus 1 of omega over 1 minus omega squared. You all agree with that? And that's the phase. By the way, what's the phase at 0? Well, at 0, what is the value of omega over 1 minus omega squared? When omega is 0, it is 0, right?
0.
What's the inverse tan of 0? 0.
0.
Yeah, thank God it is. But that, and then you can go ahead and wrap this around. If you had omega go to 1, what do you have? Well, you have 1 over 1 minus 1. That's infinite. What is the inverse? And it's a minus sign. What angle gives you infinity? Tangent of what gives you infinity? 90, right?
90, yeah.
Okay. So that's how you go about doing that problem.
Okay.
Okay.
I'm gonna go ahead and dash out of here, but thank you for your time.
No, I'm trying my best. I feel for you guys. I feel for the professors. Yeah, I think I might have mentioned this, that, you know, one of our faculty members in building science passed away. He was a lecturer, Roger Rice. I didn't know him personally. We've got, I think, 6 or 7 people that are mainly staff that are infected with COVID-19. They didn't give the names or where they're located. Nobody in electrical or in computer engineering, according to Dr. Elms yesterday, there's nobody that we know of that's tested positive for it. I did have a friend's son, and he was made the paper. His name is John Braswell's son. I forgot his first name. I know the kid. He went out on a ski vacation. That person, or what is it? Is this was this somebody trying to get in, or was there
It's just a chat message.
chat? Sorry, let me see what's on chat. Oh, well.
Hey, sorry, I had plotted that function in Wolfram Alpha, and I was going to ask you, basically, how do I interpret the graph of that?
Good question. Why don't you share your screen? Here, I'll give you,
Okay.
because you are a co-host. You can go ahead. Just share your screen so we can all see it.
Okay, can you guys see my screen?
Yeah.
Hold on for a second. I got to move all of you guys off mine. All right, go ahead.
So here's the plot, and I was just trying to figure out, like,
What's the
so
real
this
and
is the-
yeah, they're showing real and imaginary. What you want to do is plot the angle.
okay, so this is just plotting the magnitude here. So
No, it's real and imaginary. It's separately plotting the real and then the imaginary part. What you want is the angle of that.
okay,
You don't care what the real part or imaginary part is. You want the angle and magnitude.
Right.
Isn't that the real and imaginary part? Or am I reading this wrong?
Yeah.
yeah.
Yeah,
For
you
some
don't
reason,
want
it
that.
always
You want the angle.
So
Uh,
in that case, would you just plot the negative inverse tangent of omega over 1 minus omega squared?
Yeah, exactly.
can you say the function one more time, Jeff?
All right. Yeah. It's you're wanting to plot negative tangent. Well, negative arctangent.
What I think I can do this fairly quick.
Okay.
Omega divided by 1 minus omega squared.
1 minus omega squared.
Correct.
I kind of like talking to people. Right now, I'm getting tired of talking to myself and my dog. My wife's at work.
Okay.
Yeah. So the top one is the plot of the magnitude, and the bottom one is the phase. Yeah, I'm not sure how to actually interpret the graph.
It plotted the real and imaginary again.
Yeah, for some reason, Wolfram Alpha always does that.
Like it looks like the first graph is the real and the negative real part. And the second graph looks like imaginary and negative imaginary.
So I guess my question is like, so here you see there's like, I guess the highest point is at 0. So what exactly does that mean? Does that mean it has a strong frequency there?
What? I'm plotting it myself.
Okay.
Give me 1 second here. I got it. Here. I think I've got this. I'm going to take back my screen for a second.
I need to go as well, but thank you again for helping.
Sure. Can you all see this on my screen? I just used Octave to plot it. Can y'all see it? No.
Yeah,
Still
you have to
showing
share a
camera.
screen first.
All right. Now it's 0. The phase is 0, right? This is the phase, right?
I think you have to share a screen.
Oh, it's not shared? Sorry. I thought it was. I'm sorry. Here we go. Can you see it now?
Yeah, we can see it now.
Yeah.
All
Okay.
right. At 0, it's 0 degrees, right?
So
And
this
I
is
didn't-
is this the phase?
Yeah.
Okay.
It's 0 degrees. Keep going on it. What happens? It goes up, 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 up. And when it hits 90, it's zooming to infinity. Now, I didn't parse it that it's going to go, or I'm sorry, the angle's going to go to 90 degrees. Pardon me about that, right? So this would be pi over 2 if I actually did a pi over 2 marker on here. But that's the phase. I hope you all can see this, right? Isn't that the same thing as the phase on yours on Wolfram Alpha?
No, I think mine did something completely different.
For phase, isn't this if you look in here, you see omega, and then this is the inverse tan. Oh, it's minus. Sorry, it's the minus. I need to do this over here. Put a minus inverse tan. Matter of fact, I'm going to do that, but I'm also going to do one other thing. I'm going to not 200 points. Make it 800. And I need grid on. Hold on.
So for these types of problems, are you really only interested in the phase, or are you also interested in the magnitude as well?
Well, you need both, right? If you're going to do it, if I want the magnitude of the third harmonic or fifth, you'd have to get the magnitude. If I ask for the phase of the third or fourth or fifth harmonic, then you have to look inside that cosine operator and take the phase of C of n and the phase of h at that third harmonic or fourth, right?
Right.
Okay, so both are important. Everybody's, I think, Ruth left, right? We've got 5 people.
After this, Dr. Baginski, could you do an op-amp problem?
Yeah, I can do an off-amp. I'm about ready for some lunch too. An op-amp, do you have one in mind?
There's not too many of them, so I was thinking, could you do one with like an impedance, I guess, or just like condensing them like a Z1 and Z2, like what we did kind of for one of the old quizzes. I know that's not really specific, sorry.
I mean, with op-amps, it's really, the only thing an op-amp is something that allows no voltage to develop between inputs by feedback, and there is no current into the op-amp. So those are the only 2 rules you need to follow, and then everything else is seamless. With operational amplifiers, how about this? Come up with a problem. Here's an op-amp, then I'll put 2 op-amps, right? Like this. On the input of this one, I'm going to have this and a capacitor. I'm going to ground that. That's the negative. This is the positive terminal. Then I'm going to come over here.
Slide it down a touch, and I think it's out of focus as well.
Yeah, I tell you what. Let me get a different pen.
There we go.
And let's just worry about this one for now. So I've got a resistor and a capacitor.
Okay.
And then I have an inductor and a resistor. All right, there's an output. I take, I'll forget that one. Make that an L and an R and a C, and put an input, plus the minus X of T. And I want to know what Y of T is. There's a problem for you, right? Well, the real thing you want is a transfer function, don't you? I mean, if we get the transfer function in the estimate, game on, it's over. Y'all agree with that? So what I'd like to do is I'll go to the S domain. And I put in the impedances. Do y'all see this? All right. After I put in the impedances, what do? I usually call the impedance between the negative and the output. I'll label that as Z2. And the impedance here, I'll just label Z1.
Mm-hmm.
Y'all with me on this one?
Mm-hmm.
Yeah, that makes sense.
Now I can say that my H of S is Y of S over X of S, and it's pretty straightforward. That's going to be minus Z2 over Z1. Y'all agree with that?
Mm-hmm.
Right? So what is Z1? Well, Z1 is 1 over what? 1 over R plus SC, correct?
Um,
1 over the first impedance plus 1 over the second impedance, right? Like
Yes.
resistors in parallel.
Okay.
You all with me?
Yes. So
Jeff?
it'll be 1 over R plus CS.
All right, now I'm going to do one other thing too. I'm going to get rid of that coefficient of S, so I'm going to divide top and bottom by C. So I have 1 over C, 1 over RC plus S.
Mm-hmm.
Guys, you with me?
scroll it down a little bit.
I got that. Y'all, you agree with me?
Mm-hmm.
All right, what is Z2? Well, don't everybody talk at once. It's 1 over R plus 1 over SL, isn't it?
Yes.
Guys, they're not.
Yeah, I'm trying to catch back up.
I'll give you, go ahead, catch back up. Come on. Autofocus. Just with me?
Okay. Yeah,
All right, what am I gonna do with this guy? Anybody?
make it negative, right? Put it in the numerator.
Well, not yet. What do I have to do to make it a little more convenient?
Trying to multiply top bottom by L, maybe?
S by S
Or S.
first, right? Gets rid of that, and then what do? We're gonna multiply by R, right? So we have SR, right? Over S plus R over L, correct?
Right.
Okay.
What's next, Ruth?
I think she's gone.
Huh?
I think Ruth is gone.
Yeah,
I'm
Ruth
sorry.
isn't here.
Oh, I mean, which next Lydia? Sorry.
What were you asking? Sorry.
Next step. I want this. What am I going to do? I'm simply going to put
Plug it
Z1
back.
here and put Z2 here, right?
Right.
And what do you get? Well, I got Z2 is this. I'm going to run out of paper. It's going to be RS over S plus R over L, right?
Mm-hmm.
Put a minus sign. This is going to be, forget that right there. And then do what? Divide it by Z1. Well, Z1 is this, right? So that's going to be S plus 1 over RC here over 1 over C, or just multiply the whole thing by C. You hear me? Guys,
Right, yeah.
are y'all there? Turn on
Uh,
your mics so I can hear some chatter.
oh, 1 over C. Okay. Yeah, that makes sense.
Now what am I going to do? Well, look, y'all see that I have an S plus R over L. That's a pole, right?
Mm-hmm.
Right.
I've got an S squared and an S 1 over RC. Now I can go ahead and do a partial fraction expansion and find out what on earth is going to happen, right?
Right. And then you can find your, or A and B, or what have you, and then just solve for,
Well, yeah, I mean, by the way, this is an H of S, correct? If we wanted it, the magnitude and phase for a Fourier series problem, we just replace S by J n omega naught. And frankly, if you wanted to find an output, if I had a given input, suppose X of t was like e to the minus 3t u of t, you take the transform of that, multiply it by this filter, this H of S, and then you'd get the output. You'd have to do partial fractions, right? Now, I know Wolfram Alpha can do a lot of the inverses and stuff, so I'm very cognizant with tricky problems that you can't use Wolfram Alpha for. I'm hoping to. And I'm trying to eliminate cheating, but I mean, some of this is going to be on your honor. I don't want you on the internet, but I want you to do these things with all the available resources you have with your books. And but I'm not. I mean, some of this we just have to try to trust. And I don't really want to use honor lock because multiple choice tests for engineering, it defeats engineering. I think you can be a good test taker and know very little about engineering, in my opinion.
There was one problem I had. I need to look it up really quick or double check on the homework.
All right.
Let's see. Sorry, I should probably pull it up beforehand. I think it was 2.18, I guess, for question part with, yeah, 2.18. It was a block diagram convolution question.
All right. 2.8. Did you all get a chance to fill out those student evaluations of teaching? Okay, I try to get some feedback. I'm trying to get feedback on, you know, I'm going to have summer slides prepared that I can reference. I'm just reference. I'm going to still write things set up a little better with my document camera. But I'm learning. Now, GoFu, I guess, is using just a tablet to write on, Dr. Nick. And, you know, he's one of the, this is my opinion, but I think he's one of the best teachers you're going to come across.
He's really good.
Yeah.
What kind of tests did he give you?
Currently, it's an online through Canvas test. Like some of them, you have to like take a picture and just drag it in.
Okay, but he did have you work it out, right?
It was
for most of it. He limited the actual like physical writing or drawing problems to as little as he could. I think there was about 3 of them on the last test. And the rest of them were like, I guess, multiple choice or fill in the blank, like, you know, where you just get an answer like 3.2 volts or whatever. You put that into the box or whatever. But we only had to take pictures of 3 of the problems where we had to actually like design the gates, things like that.
All right. Which problem was it again? Lydia?
2.18.
3, you said.
2.18.
2.18. All right.
Yes.
So it's this one?
Yes, sir.
All right. For this one, show that the overall impulse response of the interconnected system is 0. Well, what this amounts to, and this is how I do it, I'm going to say. You have this, right? H1, H2, correct?
Yeah.
You know what the transforms of these are, right?
Yep.
All right, I'm just telling you how I do this. I take a look at this. I take the transform of this first one, multiply it by the transform of the second one, right?
Okay.
Mhm.
Yes.
Now, you don't have Laplace transforms here at that time, but I'm telling you this is how you do it. Then you come down here, it's H3 and H4, so you take the transform of this, and multiply. Then you add them together, and you're going to add together, and they're going to add up to 0. And
Okay.
you can do it. I mean, at least I think they add up to 0. I can't say that for authority, but I'm assuming you have a book, so 2.18 is available. I need to take H1 times H2. So the first one is just 1 over S plus 1 minus 1 over S plus 2, or S plus 2. That's H1, and it's times H2, so it's times 1 over S plus 3. And then I have to add to that 1 over S plus 1 times 1 over S plus 3 minus 1 over S plus 2. I'm just taking the transforms, H1, H2, multiplying them down here. That's H3, H4, multiplying and then adding them. Let's see what they add up to. Y'all follow me on this one?
Yep.
All right, just take a look at this by itself and go ahead and get a common denominator and fuss with it a little. So in the inside, I have what? S plus 2, and then I have S plus 2 minus S plus 1 over S plus 1 times S plus 2 here. And all this is divided by S plus 3. That's the first part, correct? Minus, and then it's going to be 1 over S plus 1, right? And then I'm going to have S plus 2 and, minus quantity S plus 3. And it's all over S plus 2, and then S plus 3, correct? Now, y'all agree that the denominators are the same, right?
Yep.
So when I look at the numerator, what happens here? Just do the math on this one. I
They
have
just-
S minus S is 0, correct?
Yep.
And 2 minus 1 is going to be 1, right?
Right.
That's minus. Now go and do the math on this one. I have S minus S is 0, right?
Right.
And this is going to be 1. That's
-1.
That's going to be minus 2 times. Did I do that right?
Yeah.
Yeah, that's
That's going to be wait a second. Oh, this I had these backwards. This should be S plus 3 and S minus, or S plus 2. So that's going to be 1 with a minus sign is 1. So 1 minus 1 is 0. And that the only thing is 0.
Okay. That makes sense. So you take the transform and then you solve the transform.
I would do it with transforms. I wouldn't fuss with convolution. You can convolve them, but it's an irritating little thing.
I have 2 more questions. They weren't in, sorry for all this stuff, but
Go ahead.
weren't in the book, but it was a DTFT of find the inverse DTFT of the following x of omega. It's homework 23 part 1.
Just tell me what it is.
It's x of capital omega is equal to capital of omega pulse of width pi of capital omega. and find
Okay.
the inverse DTFT of that.
All right, let me ask you this. What is P pi of omega? What does that transform to?
Tau sinc.
Remember, you know you're going to have what? Normally, I always tell people, think of duality, go to the continuous time domain. And you know if you have what? A pulse of with tau of t, it always goes to tau, right? Times the sinc of omega tau over 2, correct?
Mhm.
Now, use duality. That means tau times the sinc of t tau over 2 goes to 2 pi here, pulse of with tau of minus omega. It's even, so just plus omega, and then divide by 2 pi.
Well, it will be 1/2 of sinc of.
Oh, you're doing it already. Well, yeah, and the thing about this, we can use this relationship because we're still within the range of plus or minus pi, right?
Yes.
All right, so now I can say that for mine, the P pi of omega goes to what? Just 1/2, correct? Times the sinc of, and now tau is pi, so it's pi over 2 n, right? Okay, we've got that relationship. Next, tell me about this. If I have x of t goes to x of omega, right?
Could you move the paper down?
Yeah. If x of t goes to x of omega, what happens when I have omega x of omega?
You take the j and the derivative, multiply.
Actually, what is it? It's j omega here is the way you usually see it, is dx dt, correct?
Yes.
I'm trying to, what page are those on in your book? You guys know what pages?
Are you looking
Transforms?
for the DTFT transforms?
No, this is going to be continuous time. The property will be the same. You get. Oh, this is on page 229 for continuous time, what I just showed you.
Okay.
And so if you had just omega here, there would be a minus j here. And for DTFT, it'll be the same thing. I don't know that property. Let me take a look. I don't actually know if you said.
If you're looking for the properties, it's on page 395.
$395, you said?
For DTFT properties.
I don't see what I'm looking for there, though. Do you?
I don't either. So,
doesn't matter. Here's the deal. Y'all know this one, right?
yes.
All right. Now, if x of omega was this, right? Then if I multiply by omega, what I'm end up going to do is taking a derivative of this. Just follow me on this. If I have this function, if I have p tau of omega, I know that goes to
Write it down.
p tau of omega. I know that goes to tau, right, over 2 pi times the sinc of t tau over 2, right? Now, that is continuous time. but it would work for discrete, for discrete time as well. If this was capital omega, we'd still just replace t with n, correct?
Mm-hmm.
All right, now in continuous time, what happens if you have omega times p tau of omega? Or make it j omega, make it j omega. What do? This is like your
Take
x of
this
t,
one.
this is like your capital X of omega, right? So if I had a j omega there, the relationship over here would be a derivative with respect to t, continuous time, of tau over 2 pi times the sinc of t tau over 2, correct?
Yes.
All right. Now, once you do that derivative, right? Once you do, and you would have to replace sinc with sine of t tau over 2 divided by t tau over 2, right? And then you would have to do the derivative, correct?
Yes.
I mean, maybe the derivative of the sinc function. I don't know off the top of my head. But when you do that, then what would happen is, this is still within from minus pi to pi, as long as tau is less than 2 pi, correct?
Mm-hmm.
All right, then you simply take this, you divide it by a j, so it's making a minus j here, times this, get rid of the j, and then replace the small omegas with capital omega, and you would replace t with n.
Mm-hmm.
Okay?
That makes sense. Okay. So you would have to convert it into a sine function and then
Well, what is sinc? Isn't sinc sine of x over x?
yes, sir.
All right, if you take a derivative of this, take derivative of sine, you're going to get a cosine, right?
Yes, sir.
Divided by x plus sine of x divided. I got to take this down. Hey, Jim. Yeah. Oh, that was a- All right. Are you with me?
Yes, sir.
Yep.
Go ahead. Anybody?
So I guess in this case, it will be, since it's sinc of nt over 2, it would be sine of nt over 2 divided by nt over 2.
Well, you take the derivative in a time domain, right?
Oh, no, that's the derivative. If you're converting from a sinc to a sine and then,
The only thing, yes, like this would be, the sinc of t tau over 2 is just sine, right, of t tau over 2 divided by t tau over 2.
okay, that's what I thought. Thank you. That makes sense. All right. I was just wondering where the negative j came from mostly.
Or what?
The negative j came up from, but
Because
like,
it was over here.
dividing by, okay, that makes sense. It answers my question. Thank you.
Mm-hmm. Oh. I gotta get back at the call. I gotta also stuff.
Okay.
We good?
Hopefully.
I think so.
Spencer?
We'll certainly
have a
find out, I guess.
This is one of those things that random signals and systems is probably a little more complicated in this course. It's dependent on how it's taught. Dr. Reeves is going to teach you everything in that course. Well, a lot of it relies on this course, and a lot in communications relies on this course as well. These are sequential. You're going to get these in the next couple of semesters. And then most of your senior level courses, unless you do fabrication, are very reliant on this. This course and circuits are key to everything you do from here on. If you don't have these down, especially this one, then you're really out of luck in a lot of courses. I enjoyed this course. I enjoyed teaching it because most of the stuff I'm teaching it from the perspective how I'd want my students to be taught when they come into radar and EMC or microwave or EMAG. And unfortunately, there have been teachers who are very slack and taught this. And people get through it and they have no comprehension of Z transforms or Laplace transforms, and those things are crucial. In electrical engineering, you're never going to pass through electrical or computer engineering to get through it unless you have a pretty good understanding of this along with circuits. Now, a computer science major still needs to know this, if he's doing anything that has to do with data analysis and correlations and stuff like that. One last thing I'll give you, when you see correlation functions that you're going to be getting, that's the same thing as convolution. So there's a lot of similarities. I mean, a lot of things here you're going to hear referenced with a different terminology. I enjoyed teaching. Of course, I'm sorry I didn't do this way. When everybody doing remote learning.
Yeah.
Yep, it was fun while I was back in Auburn, but it's definitely been a transition. So,
Well, you're still in Auburn, right?
I still am in Auburn, but I should say on campus. So,
You know, I went up and I was driving on campus, I think it was Sunday, and I drove by Ruth and her boyfriend taking a walk. We did a walk by the agricultural, they have an area by the Arboretum where they have planted fields, walk through there. And then there was the beacon, the pond over there. It's a pond by an ag heritage park where that red barn is.
Yep.
And I don't know if Keysville Park was closed down or not. I think Opelika's city parks are all closed.
Yeah, they completely closed even the disc golf course and everything over at the Sportsplex.
Well, they're playing Frisbee golf over at the Red Barn, and the golf courses are open here. Now, my cousin I talked to in Pennsylvania, he told me the golf courses were closed around York, PA, which makes no sense because golf's the one thing where you can literally do social distancing very easy. Just one per golf cart, right? That's what they're doing here, unless it's a man and a wife.
It's just up to individual areas, I guess, basically. Like some places have them open, some places don't. It's just kind of.
Now they closed the tennis courts in a lot of places, but I mean they took the nets down.
Yeah, same with like Opelika, and they have pickleball now or whatever, but they shut all that stuff down as well. Like the whole Sportsplex, the pickleball, disc golf course, like they blocked off the front entry, which I guess it serves as like the Church of the Highlands or something on Sundays, I think.
Yeah, they're doing all the. I go to Covenant Presbyterian Church, and their whole session, they're Zooming everything. It's like Wednesday night and Sunday school. And the problem with that is that some people are not that up to date with technology. And I mean, they don't even know what you're talking about when they say an iPad. They can't Google it because they don't have a computer to use. Everybody thinks that, and then this is a lesson I learned. Don't assume that people have the same technology that you have. Don't think they have an iPad or a tablet. They're only means of communications, and sometimes it's not even one of these phones, it's a landline, and that makes it tough.
Well, that's been the big problem in Montgomery public schools, is that a lot of the kids there don't even have internet access. So to go
well,
to
how are they
remote,
dealing with that then?
They're trying to set up like mobile buses to act as like hotspots, basically.
Oh, I want to tell you one thing. You can take your phone and make it a Wi-Fi hotspot. So, I mean, I'm assuming they have a computer. I mean, if they don't have a tablet, then or something that can connect.
It's outrageously priced. I know that I pay it's like per half a gig or something, and it's ridiculously overpriced.
For what? A Wi-Fi hotspot?
Yeah, for AT&T. If I want to turn my phone into a Wi-Fi hotspot, it costs me outrageous money. It's essentially the same thing as 10 years ago when you would be like roaming. when you get like roaming charges. It's just now they give you all the calling and texting you want, but now they charge you for Wi-Fi. It might vary different plans or whatever, but I know for a fact, like when I had Verizon and now that I have AT&T, like both of them charge exorbitant amounts of money for turning your phone into a hotspot.
Hey, can you hold on for a second? I'll be right back.
Well, I'm gonna run outside real quick then.
Oh. All right. Give me a second here.
I think Jeff went outside for a bit.
I'm with you on that.
Yeah, just 2 more days and I'll be done with finals, so it's gonna be nice.
Take a nap.
Yes, sir.
Are you 21 yet?
No, sir. Next year.
Okay. You can't legally have a glass of wine or a beer or anything like that.
Not yet.
I tell you, the one thing that has stayed open, no matter what, is liquor stores. I realized that there's tax revenues, and the taxes are right now are in the city of Auburn. The last month, it's about a $10 million shortfall. Now, this is the city of Auburn, but statewide, you know, they're getting clobbered. People aren't driving. The gas taxes are coming in. There's not a lot of stores.
Yeah.
I mean, the amount of revenues they get from taxes is probably tank. And I've mentioned this before, but we didn't have a meeting today, but on Monday, our athletic director was talking about all the things they're toying with for this year's football season.
Really?
Apparently, the NFL has decided to have all their games in like 2 stadiums that will be empty and just is at least a possibility. And they'd house the teams there. They would have like a shelter and a quarantine area. I was listening to somebody talk about that. Now, NFL and the SEC, I mean, the revenue stream for college football is immense. I don't know what's going to happen to the local merchants if there aren't people.
Oh, that's going to be really rough.
Yeah, I know there's huge economic fallout in Auburn or any of the major small city college cities, I guess you could call them. I don't know, towns, I guess.
Any industry that's based on service to the crowds for sporting events, be it baseball, football, basketball, they're going to get crushed. I mean,
Well, I mean, I know a lot of like the local businesses here, even, you know, they might make half their revenue from the 3 months of football season for the whole year. So when you cut out the massive crowds that are coming to Auburn for home games, then, you know, they're going to suffer.
think
Like
about
my
Tiger
buddy
Rag.
is actually, he's the head chef for one of the fraternities on campus. And he's basically essentially just completely out of work since all the kids are home. None of the kids are at the frat house, so.
Yeah, they've had to, like bartenders and waitresses, they've all been laid off.
I guess she just extended the non-opening till May 15th. KI did.
Wow.
Hey, let me tell you something. Georgia opened, right? Supposedly.
Yeah.
And they're keeping a keen eye on Georgia, because if all of a sudden they get a spike in cases and they start to run out of ventilators like they did in New York and other places, and people die at home because they literally don't have a ventilator for them, you're going to see probably a federal order mandating quarantine until a vaccine or something like that's available. Because this is, I listen to people talk about this, how, well, they're really hurting the kids because their group immunity, herd immunity isn't growing at the rate it should. I'm thinking to myself, have you really thought about that? Herd immunity, when people are dying from the disease, I mean, you don't get a herd immunity to Ebola or something like that, die from it. And what they're going to do, the vaccines, the whole thing, that, when you get a flu shot, that has strains of flu that are related to H1N1, SARS, all the stuff going back in. So you will have an immunity to the known common diseases. Some you can't. I mean, you can't become immune to HIV. It's an impossibility right now. They're trying. Things like that. Like immunity to a bacterial infection either. What I understand. Well, guys,
Torn between the two. I mean, either way, you're going to have, on one side, you have people getting infected and dying, and other ones you have people essentially starving because now they're out of business.
Well, not in this country. The one thing they've got, and they've done it right from what I can tell, they have a tremendous amount of money available to lower income people and to people out of work. And I think to the tune of 2 or 3 trillion right now that they've already have outlays for. So, I mean, assuming the person has availability to get news, they can be directed or can call the police or call some emergency management. They're taking care of people. Nobody's starving. Nobody has to, put you that way. And they're even doing holds on like rent and all this stuff. I don't know if you've read about some of the problems. Restaurants, like a lot of the restaurants, they're getting a pass on the rentals of the rent that they owe and stuff.
But, well, the first outpouring of relief for small businesses got all eaten up by big businesses.
Yeah.
So they ran out of money. So they got some more money together, and they're starting to put that out as well to help. But I mean, also,
I don't, this is one of those things. Federal versus state are two different things, and the state of Alabama, especially for farmers and stuff, I think they've done a lot to give relief to the people in the agricultural area. I don't know what's going on federally on that.
Yeah. But I mean, I don't know. It's a messy situation regardless. But
there's never been a time in my lifetime that even came close to this. Even when there were measles outbreaks or SARS or H1N1.
And I don't know. I guess I'm kind of opposed to the whole $600 extra unemployment thing. It just seems a little odd.
Well, when you're dealing with people that really do study economics and they understand the forecasting models and what works and what doesn't, these are federal people usually. They've been doing this for a long time, and like the Federal Reserve is, I got problems with the Federal Reserve, but they do, the people that manage them and stuff, they do a pretty good job of stabilizing the overall economy in the worst and best of times, assuming that the federal government doesn't get in their way. I mean,
what's the incentive? What's the incentive to go back to work when you make 3 times as much on unemployment?
Well, that's never true. You'll never ever be given more money if you're unemployed than you made when you were employed.
You are with the new stimulus thing. You are. You're given your unemployment raised to 100% of your income, plus an additional $600.